23. This is the last new topic. And then we can start our test review. Maybe we'll start today since this will take a whole period, but maybe we can pick out some review problems. But okay. So far, we've been doing limits as we approach a real number. So approaching 3, approaching 5, approaching -5. We've also been doing one-sided limits, approaching 3 from the left, 3 from the right. But we talked about how the one-sided limits, many times, it's not going to be any different than finding the limit, right? We're always going to follow the same steps. We're always going to do direct substitution. And then if there's a vertical asymptote, then and only then do we do something with that one-sided limit that is different than other problems, okay, where we play with decimals. But many times the one-sided limit doesn't mean anything. It's just there to distract us. So if the limit exists, then the one-sided limit will be the same as your full limit. All right. Now we're going to switch gears a little bit because now we're going to be approaching not a real number. This is approaching infinity. So if it's approaching infinity or negative infinity, we're basically concerned about, how is the graph behaving as it exits from view? So if the graph looked like this, then if we're looking at positive or negative infinity, we're looking to see where are the arrows headed. Is it flattening out towards a horizontal asymptote, or is it going up or down without bound to positive or negative infinity? So today we're talking about these end behaviors. We're looking at how are the graphs going to look as it exits from view. Okay. So all these are going to be limit as we approach infinity. And the way we deal with infinity is we don't plug in anything. We just simply go and look at the degrees, the highest degree between numerator and denominator, and compare them. Okay. So here are the three main categories. If the numerator degree is less than your denominator degree, meaning that your denominator degree is higher, your limit is always going to be 0. Or in other words, your horizontal asymptote is going to be at y equals 0. So we're going to be tying in the limit with horizontal asymptote. Right? If our limit approaches a real number, then we can think of that as a horizontal asymptote, right? That means the graph is flattening out. And if it flattens out, then we can put a dotted line and it's going to basically be the horizontal asymptote. Second condition is if the numerator and denominator degree are the same. That means we've searched the highest degree in the numerator, and then we search for the highest degree in the denominator. And if they are the same, that means they're both moving at the same rate, and they're going to be flattening out according to the ratio. So we just find the highest degrees, and we just pull the numbers in front. We don't care about any other degree that's less than our highest degree. And that's our limits, but it's also our horizontal asymptote. If it's asking for a limit, you can say 5/2. If it's asking for a horizontal asymptote, then you will say y equals 5/2. Horizontal asymptote is an equation, so we have to indicate that with a linear or something in equation form. Let me give two scenarios from 1 and 2 that it doesn't matter if we're approaching positive or negative infinity. We're always going to either be 0 or we're going to be the ratio. So here's another example. Limit as x approaches negative infinity of 5x squared over 2x squared minus x plus 1. This is also 5/2. So I want to point out that it doesn't matter if we're going towards positive or negative infinity. It's going to be the same horizontal asymptote. It's going to be 5/2. So sometimes I feel students, they overthink it and they see, oh, wait, there's negative infinity. And they end up changing the sign of that based off of the positive or negative infinity. So the fact that it's positive or negative infinity just means there's usually just one horizontal asymptote. So don't change the sign based off of whether we're going left or right, which is always the ratio. Now, there's an exception to this rule, and we'll talk about that on the next page. But if we're seeing something that is kind of like a normal rational function, then it's just going to be the ratio and no change in signs. Finally, if your numerator degree is greater than your denominator degree, then we don't have a horizontal asymptote, meaning that the limit doesn't exist. But we have to specify where the graph is headed. So, so here, this example, we're approaching infinity. Degree 3 versus degree 2. Degree 3 is higher than degree 2. Also, if you think about increasing the value of my numerator and denominator, both are approaching infinity, but you can tell that the x cubed is growing at a faster rate than the x squared, and eventually that gap is going to continue to widen. And because of that, this fraction is getting larger and larger. And if it gets larger and larger, it's either going to go up to positive infinity, or it's going to go down to negative infinity. So we have to decide which way the graph is headed. As it exits from view, is it going up towards positive infinity, or is it going down towards negative infinity? And the way that we test is we choose a number in the direction that we're headed. So if we're going to the right, I want a large positive number to kind of give me an idea where the graph is headed. And an easy number for us to test, you don't have to test this number, but I think that's an easy number is 100. That's a relatively large number and should be relatively easy to plug in. Now, when we plug in, don't feel like you have to find out what this number is. That will take a long time. All we care about is the sign. So if I plug 100 into the numerator, am I going to get positive or negative? Positive. If I plug 100 into the denominator, also positive. So that means this graph is, as it exits from view, it's going to go towards positive infinity. So this is the only time where you're going to have to consider that there could be a change in signs. And if we're approaching negative infinity, that means we're moving off the grid towards the left. Then we can test what number if we're approaching negative infinity. We can also test an easy number. We can test negative 100. Yeah, so either positive or negative 100 if your degree in the numerator is higher and if you're approaching either positive or negative infinity. So I think by themselves, these are not too hard, but you can imagine a problem where everything is mixed together. You have real numbers, you have one-sided limit, you have vertical asymptote, you have horizontal asymptotes. And so it's easy to be like, wait, where do I, what's my first step, right? So we're going to put it all together over the next over the next few days. But the big picture is if you see a real number, direct substitution. Okay. If you see infinity, compare degrees. So if you can have those two categories clear in your head, that's a good starting point, because then we can figure out the rest from there. But it's important that we know where to start, right? Your first step is, I think that's the hardest part of all these problems. If you know what the first step is, then everything kind of falls into place a little bit better. Okay, notes, horizontal asymptote is a description of end behavior. It is not a boundary that the graph cannot cross. A function can never cross a vertical asymptote, but it might cross a horizontal asymptote. So you may have a graph that look like this. And the dotted line for horizontal asymptote is not a restriction. It's more of an end behavior. It's giving us an idea where the arrows are headed, but even though we see the dotted line cross all the way through, it doesn't mean that the graph can't cross it. It's not a restriction. The vertical asymptote is a restriction, but horizontal asymptote is more of a dotted. So really, you can just think of it this way, where the dotted line only applies as we exit the graph. That dotted line is not really meant for the middle of the graph, because the graph can cross it and there's no issue. Okay, so let's practice the three conditions or the three possibilities of results if we are dealing with if we're approaching positive or negative infinity. We know that if we're approaching infinity or negative infinity, we always compare degrees first, and then from there we can decide which category we're in, and then what our answer will be. Okay, so we're approaching infinity, so we don't plug anything in, we compare degrees. What do you notice? Good. Numerator is higher than the denominator, which means this is in the third category, which means that this fraction is getting larger and larger. We just don't know which direction it's headed. It's getting larger towards positive infinity, or is it getting larger towards negative infinity? And so we can test, right? What is a number that we can test to decide where the graph is headed? Test 100, yeah, because we're headed towards positive infinity, so we're moving to the right. A number that is large on the right side of the graph is 100. So if I plug 100 into the numerator, positive or negative? Positive. Denominator is also positive, so 2 positives makes positive. So positive 30. All right, number 5. Same expression. Numerator degree is still higher, but what's different about this? Yeah, so therefore we're moving left, right? We're moving off the grid towards the left. So what number can we test as if we're moving left? Yeah, x equals -100. Yeah. Okay, so numerator, plug in -100 for the numerator, we still get positive, right? But what about -100 in the denominator? Negative. So positive over negative is negative. So all right, number 6, approaching negative infinity, compared degrees, right? What do you notice? They're equal. Therefore, that's a second condition, right? What's our limit going to be? Close. -3/2. Not because it's negative infinity, but because the ratio is 3 and -2. We have to take that negative and make it go with the 2. So 3 over -2. But we're not going to do anything different with negative or positive infinity. If the degrees are the same, it's just a ratio. Don't feel like you got to change the signs. It's not going to be a split asymptote. It's just going to be one asymptote. So just -3/2. Number 7, same expression, just one is going to positive and one's going to negative infinity. Are we going to get a different answer? Same answer, right? So just wanted to demonstrate to you that doesn't matter if we're going positive or negative infinity. If the degrees are the same, it's just a ratio. We're not going to change signs because we're going positive or negative infinity. We only have to worry about the potential for changing signs if the degree is higher than the numerator, and we got to test either 100 or -100. All right, number 8. What do you notice? Denominator is higher, which means this is, I think, the easiest scenario. It's always going to be what? 0. Yeah. And if we think about it this way, where if both are approaching infinity, but the denominator is growing faster than your numerator, so as your denominator is getting faster, larger than your numerator, that means your fraction is getting smaller and smaller and smaller, and it headed towards 0. Okay, try number 9, and then we'll talk about it. Hey, what you guys get for an answer? Negative infinity. Okay. So we know our numerator degree is higher. So we know it's either positive or negative infinity. We know this fraction is getting larger and larger. We just don't know which direction the arrow is headed. It's negative infinity, so that means we're moving left. We want to choose a number in the direction that we're headed. So we'll test -100. Numerator, we get negative. Denominator, we get positive. So different signs indicate negative infinity. Okay, any questions? All right, back page. And this back page is more, these are kind of smaller topics, but we put it all together in the same section because these are all limits approaching infinity. So these are just different scenarios that we want to go through. So this is kind of a strange situation because most functions don't look like this. So I want to talk about it. You see how this function looks a little bit strange, right? Because there's a radical on one side, and this is not your typical rational function that we're used to seeing, right? We're used to seeing just, 3x squared plus 2 over 4x squared plus 5. So if you see a radical either above or below, this is going to be one of those, the graphs will look a little different. So the problem says, find the horizontal asymptotes. And I just want to show you by starting with the fact this is what the graph looks like. You can tell that if we're going towards positive infinity, it does have a horizontal asymptote, but this is a positive y value. But if we're going to negative infinity, there's a different horizontal asymptote, right? This graph is headed towards a different y value. So I just got done saying that, if we're going positive or negative infinity, if the degrees are the same, it's the same asymptote. And now we're breaking that rule here, but it's because we have this function that has a radical that is kind of changing the way the graph looks. But I want us to explore two things here. We're going to find the limit as x approaches infinity. So we're going to figure out why the graph is doing this to the right. So 3x minus 2 over square root of 4x squared plus 5. But let's follow through with the rules that we learned from the previous page, right? If we're going towards infinity, we're going to compare degrees. What's the degree of the numerator? 1, okay? What's the degree of the denominator? It looks like it's 2, but after everything is said and done, what is it going to turn into? Why is it degree 1? Square root, right? We know square root of x squared is going to make it come back down to degree 1. So therefore, is there same degrees here? Yes, degree 1, degree 1, degrees are the same. So we're just going to take the ratio of the coefficients. So numerator is 3. What's the coefficient in front of my variable below? Close again. It's going to be that root 4. Okay. The x squared is impacted by the square root, and the 4 is also getting impacted by the square root. So what's square root of 4? Just 2. So 3 over 2. So therefore, we have a horizontal asymptote at y equals 3/2 if we're exiting the graph to the right, and that is how the graph is showing. Now, something a little bit different if we're going towards negative infinity. So let's do negative infinity and write down the exact same expression. Same idea, right? We're approaching infinity. We know we're going to compare degrees. Degrees is still the same. Numerator, denominator, same degrees. 3 is the coefficient. Denominator is root 4. So, but something a little bit different about negative infinity is that square root and the squared is going to do something a little bit different in terms of the signs. So imagine plugging negative infinity in, or let's say negative 100. Imagine plugging negative 100 into the numerator. Am I going to get positive or negative? Negative. If I plug negative 100 into the denominator, what am I going to get? Positive. So what this is saying is that if we're approaching negative infinity, that radical is going to behave differently than that x, because this x squared, what really is the x squared that's behaving differently from the x, because x squared is going to basically force everything that comes in to be positive, but the numerator is just going to take whatever sign that it gives, and so there's a mismatch in degrees, sorry, in signs, and that's going to force this to be a different sign. So that's why we get y equals -3/2. So that's why we have two separate asymptotes. You got a split asymptote because that radical on one end is forcing the graph to behave differently towards -infinity, because this is always holding positive, and then the top one is the one that's getting impacted by the negative sign. So here's the big takeaway. If you see a radical above or below, and the degrees are the same, then your horizontal asymptotes will always be opposite signs, but the same ratio. Okay. If one side is 5/2, the other side will be -5/2. If this side is going to -8/6, then this side is going to +8/6. It doesn't mean that this is always positive and this is always negative. We always figure out the sign of the positive side. That's the easier one. And you know that negative is always going to make it change signs, because that the square is going to always hold the same sign, and this is what's going to change. Okay, so this is really the exception to the rule, but we're still seeing some connections from the previous page. Okay, last topic. Okay, bottom of the page. This is comparative growth rates. We're going to be talking about different families of functions. And if I have one family of function above a different family function, above and below, we can decide which side is growing faster, and then we can quickly determine what the limit is. So families of functions grow at predictable rates in relation to each other as we approach positive infinity. This is the key thing here, is this relationship only works if we're approaching infinity. If it's approaching infinity, it's all these relationship kind of breaks down. So we're only going to be considering for positive infinity. So here are the four families of functions that we're going to be concerned with over the course of our time together. Trig doesn't really fall in these categories, so we're going to leave trig out of it. So it's logarithms. An example of logs is going to be natural log of x. Natural log of x grows at the slowest rate. It's growing, but it's kind of inching up along, and it doesn't move up very fast. So an example of logs is natural log. Could be log base 2, could be log base 3, but natural log is the one that we're going to see the most. Next up, radical functions like square root of x. Square root of x kind of has that same shape as natural log, but it's able to grow a little bit faster. So, and again, this is approaching infinity, right? If we're just looking at the initial like 0, if we're looking at small numbers, these relationships don't really show itself until we're getting to large numbers. Then, once you get past to a larger number, then these relationships in terms of their growth pattern becomes more clear. Next up, polynomials. Polynomial like x squared, x cubed, even x. Algebraic polynomial, they all grow faster than natural log or radical. And finally, exponentials like 2 to the x, 3 to the x. The most common one we're going to see is e to the x. So e to the x grows at the fastest rate. So here is our kind of like our guiding principles for these types of problems. If we're approaching infinity, okay, and again, this only works if we're approaching infinity. Let's say we had a slower growing function above and then a faster growing function below. What's going to happen to that fraction? Will it get larger or get smaller? Smaller, right? Denominator is growing faster, which means that fraction is getting smaller. And if it keeps going along that pattern, where's that fraction headed? Towards 0. Yeah. If we're going towards infinity, eventually that number is going to get so small, it's going to approach closer and closer towards zero. Okay. What about the other scenario? What if the faster function is above and then the slower is one below? What's happening to that fraction? It's getting bigger. So there's two options, right? It's either going to go bigger towards positive infinity, or it's going to get bigger towards infinity. And if we're down to two choices, very similar to the previous page, if we're down to two choices, what can we test? Yeah, test 100. And for these scenarios, we don't have to worry about testing negative 100 because this is not going to work for negative 100. I'm not going to ask you comparative growth rates for negative infinity. So it's just going to be positive infinity that you're worried about. So there's really only two options. It's either 0 or plus or minus infinity, depending on which side is growing faster. Right. So let's look at some examples here. Limit as x approaches infinity, I have square root of 5,000 x plus 1,000 all over x squared. The numerator looks a lot larger to begin with, but let's categorize each numerator falls under which family. Of these four options. Yeah, radical, right? And then my denominator is which family is that? Polynomial, okay. Which side is growing faster? Denominator, therefore, approaching 0. That's it. In that first this is in that first scenario, right? Slower over faster, it's going to be always 0. All right, example 13. Numerator. What family is that? Logs, right? It's a slow function. 2x falls under polynomials. Well, algebraic because it's degree 1 polynomials. But yeah, same either x or x squared or x cubed. They're all kind of fall in the same category. So I'm going to call this polynomial or algebraic. Again, what's happening? Yeah, also 0. All right, example 12. Numerator is exponential. Denominator is polynomial. Which side is growing faster? Numerator. Therefore, this fraction is going to head towards where or where? Positive or negative infinity. We're going to test the number. What number can we test? 100. So negative e to the 200 over 1,100 x to the fourth. Okay. So numerator is going to be what? Positive or negative? Negative. Denominator is positive. Negative over positive is negative. So negative infinity. Okay, try 14. Right, what do we see? Numerator is what category? Radicals. Denominator. Okay, which is growing at a faster rate? Yeah. Yeah, numerator. Therefore, there's only two options, right? It's either going to go positive or negative infinity. So we can test 100. All right, numerator, we get what? Positive or negative? Negative. Denominator, we get positive, therefore negative infinity. All right, any questions? Okay, we can actually start our test review early. This is the test review packet. Let's go to page 25. I want to kind of first kind of give you an idea what we've covered and what are our test topics. So the first is evaluating limits algebraically. Evaluating limits algebraic with a hole in the graph. We know that if we're approaching a real number, we're always plugging in that integer first, right? We don't do any decimals. We just plug it in. And yesterday, I think you guys demonstrated you guys are pretty good with that you're always taking that first step and then letting that direct substitution result tell you which category you're in. Are you dealing with a real number where you stop? Are you dealing with 0 over 0 where you got to go through your factoring steps or your cleanup steps with how you did on the quiz? And then if you see a vertical asymptote like 10 over 0, then you know that potentially you got to play with decimals if it's still a one-sided limit. Okay. Identify limits and order pairs from a graph. You guys did that on the quiz, and I'm going to give back your quizzes tomorrow. Sketching a function of a graph given limit properties. You guys demonstrated that on the quiz. Use continuity conditions. We've been working with that over the past couple of days. Apply intermediate value theorem. We've been doing that as well. And then these are the last two new topics that we just did. Finding horizontal asymptotes with radical and denominator. We got to go positive and negative infinity. And then we know that there's going to be two different asymptotes. You got, in this case, what are the two different asymptotes here for this example? So 3 over root 5, and then there's another one, y equals -3 over root 5. Yeah, because the degrees are the same. We're pulling the coefficients of the, or just pulling the coefficients from those variables. And then comparative growth rates that we just did, right? Exponential over radical, and it's headed towards infinity. We plug in 100. We get positive over positive, so therefore positive. So we're just kind of circling around these topics over the next few days in preparation for our test. Okay, so let's go to page 1. So here we have a piecewise function. We're going to have to first decide which piecewise function is going to have an impact on where we are, and then we're just going to go through our rules. Right? If it's a real number, we plug in. If it's infinity or infinity, we compare degrees. So start with A here. So we're headed towards negative infinity. Which graph is going to live where we are if we're headed left? Yeah, because that's less than 2, right? We want all the values less than 2. That's going to stretch all the way to negative infinity. So we're dealing with x plus 5. So what do we do when we see infinity? We do what? Compare degrees. It feels strange, right? Because there's no denominator. But if there's no denominator, we can always force a what in the denominator? Put a 1. Right. So let's compare degrees. Which degree is higher? Numerator, right? There's degree 0 in the denominator, degree 1 above. So degree numerator is higher, which means that there's only 2 options. It's either going to go positive or negative infinity. Okay, what number can we test? Negative 100. So we get a negative over a positive, which is negative. So therefore, negative infinity. Part B, limit as x approaches 2 from the left. What is slightly to the left of 2? Or approaching 2 from the left side? Which piecewise function? Still x plus 5, right? All these numbers are to the right of 2. We want a number I want a graph that is going to get close towards 2, still x plus 5. So this is approaching a real number here. What do we do with real numbers? Direct substitution, right? What do we get? 7. That's a real number, right? We get a real number. There's nothing more to do. We're done. So that means from the as we approach 2 from the left, this y value is getting closer and closer towards 7. Two from the right. Which piecewise? 2x minus 1, right? Because 2 to the right, imagine like 2.1, 2.2. Those are all within that range from 2 to 5. So, okay, 2x minus 1. The one-side limit, but we ignore that one-side limit. I mean, the one-side limit does play a role because it tells us which piecewise to use, but algebraically, we don't, we ignore it, right? What do we do with that? Yeah, and we get 3. All right, part D, potentially tricky here. Limit as x approaches 2. What do you see? We're tempted to do that 11 because that's where we see there's a, but this is only telling us what? What is this in relation to the graph? This is just a what? It's just a point. Remember, a point has no say on what the limit is, right? So is there some previous information that we can use to determine what the limit is? Does B and C help us out? So one side's approaching 7, the other side's approaching 3. What's the limit going to be? Does not exist. Yeah. I know it's tempting to want to reach for that 11 because that is where the order pair is, but that point, it's just a point, right? We're talking about the approach. The approach is the less than greater than 2 that we're looking at. So that's tricky. Just want to make sure we are aware of that. Okay, part E. 5 from the left. What do we choose? 5 from the left. Mm-hmm. Direct substitution, and we get this what? This 9. Okay. Okay, so we got started with the test review. Your homework, you're still following the calendar. We're just a little bit ahead in our class. This gives us more time to do test review. All right, come get your phones.